Okay. V2. This is V2. Sorry. V2 must be equal to Vs2 times this voltage divider formula, okay, which is R2 over R1 plus R2 kind of thing. R1 plus R2 over R2 kind of thing. Okay, this means R1, this means R2. Okay, so this is V2 and it's Vs2 times, this is R2 is 20, 30 over 20. Okay, that is what we have. So the gain factor is 1.5 Vs2. So sorry, this should be Vs2. Okay. So the first thing we get is that Vs2 times 1.5 is V2. Okay, and Vs1 is given to be 3 volts. In the book example, and Vs2 is given to be 4 volts, I believe. This is given to be 4 volts in the textbook. So from this we gather that V1 must be equal to 3 volts, V2 must be equal to 1.5 times 4 volts, which is 6 volts. Okay, V1 and V2 are 6 volts. Then you're asked to find what this voltage is over here. Okay, what is V0? Okay, in order to find V0, you have to write Kirchhoff's current law at that node over there. So we can write out the current over here and the current over here plus the current over here. And they all add up to 0. So we have V1 minus V0 over 10 kilo ohms, which is the current flowing in that direction, plus the current V2 minus V0 over 10 kilo ohms, okay, must be equal to 0 minus V0 over 10 kilo ohms. This must add up to 0. Okay, we know what V1 is, we know what V2 is, and then we can solve for V0. And V0 turns out to be 3 volts. This one I have in my notes over here. V0 is equal to 3 volts. Okay? So if you solve this equation, we get 3 volts. So are there any other questions regarding this? Yes?
Confused as to why both V1 and V2 are just 1.5. I know, obviously I know why the V2 is 1.5 as you did it, but why would the other side be also 1.5 times?
V1 is 3 volts according to the one I have here. V1 is given. V1 is following Vs1. V1 follows Vs1. This is a voltage follower.
Okay.
So V1 is 3 volts. V2 is not a voltage follower but a non-inverting amplifier. Okay, V2 should be the gain times Vs2.
Okay.
The gain turns out to be, this is my gain. Okay, this is my gain factor, turns out to be 1.5 times Vs2. But Vs2 is given to be 4 volts in the textbook. Okay, then V2 is given to be that, and then you write Kirchhoff's current law for that node in the center. You get V0 to be 3 volts. Okay? Are there any other questions regarding this? So, I can also talk about the case of inverting amplifier, but let me use the remaining 10 minutes to talk about the positive feedback and the negative feedback with respect to this diagram over here. Okay, why positive feedback doesn't work, why negative feedback works. Okay, so when we have negative feedback, it is a voltage follower, but if you have positive feedback, it cannot be a voltage follower. And let's dwell on that detail. There's quite a bit of verbal argument given in the textbook, but let me see if you can say it more quantitatively. And then this is V minus, V plus, this is I plus, this is I minus, this is R source, okay? And this is a voltage follower, and that one works, but that one doesn't work. And let's examine the reason why, okay? Let's assume that the V0 is equal to Vs plus delta, or minus delta. It has to be slightly lower. V0 has to be slightly lower than Vs. V plus would be equal to Vs because of the low current that flows in there. Okay? So if you were to look at this circuit, then V plus minus V minus, as we said before, is equal to Vs minus V minus, which is Vs minus delta, which is equal to plus delta. Okay, it's a positive number. Okay, and if we make sure that delta is small, if delta is smaller than VB over A, if we make sure that delta is small, then we are in this linear range. We operate in this linear range, and in this linear range, okay, the V out can be any value from 0 to VB. You can pick any value from 0 to VB, and in that case, we pick a value of V out equal to Vs minus delta. Okay, it operates in that range, and then in that case, the V plus minus V minus is actually a very small number. So you can operate in that mode. Okay, and if you keep making Vs larger, okay, then you will be working closer and closer to saturation. Finally, if you reach saturation, you're out of the linear range, and your VB cannot grow anymore. But your Vs can grow, okay, but your Vs can grow. So what happens is that that is not the regime that you want to be in, because if Vs grows, but VO doesn't grow, what happens, what it means is that you will be not in the linear regime, okay? You cannot make that linear approximation, okay? However, in this case over here, you could make V0 to be close to Vs, but this number delta doesn't have to be small. You can see that if I make V plus being equal to Vs plus delta because of this connection, then the differential voltage V plus minus V minus is delta. Delta can be anywhere here, okay, anywhere here, and that VO can be equal to VB, and when it's working over here, VO just is equal to VB, and delta can be quite large. Okay, delta can be quite large, and you're in the saturation regime where the linear amplifier doesn't work anymore. You can push yourself or push yourself into saturation quite easily with this negative or positive feedback system. Okay.
I think there's another way to prove this.
Yeah, how would you prove it?
So we can use that diagram which you have right there.
Yes.
Using the resistors and the expression. So now we know that R naught is very small.
Okay.
So which means that V naught will almost be equal to A into V plus minus V minus, right?
Okay.
Now now if you plug in this diagram into the op amp, there we see that V plus will be equal to Vs, right?
Okay.
Then which means my output voltage would be AVS. Now, and because of my feedback, V minus would take the value of V naught, which is equal to AVS.
Okay.
And using my op amp approximation, V plus equal to V minus, so my input becomes AVS.
Okay.
So it'll burn away.
Okay. Yeah, there is a way of saying this more succinctly. Let me see how I can say it more succinctly. That if you were to be outside the linear regime, you will give rise to a contradiction over here. So this left-hand picture has to operate in the linear regime. And if you push yourself outside the linear regime, you give rise to a contradiction. Let me see how that goes. So if you were to be outside this linear regime, then VO has to be VB, and VB, let's assume that VB is less than VS. Okay, then what happens is that this would be VB. If you're outside linear regime, this goes to VB. VO becomes VB, and V plus is still VS. Then V plus minus V minus is equal to VB minus V minus. Okay, V plus minus V minus is Vs minus V minus, but Vs has been linked to VB. Okay, but we say that VB is less than Vs. You're outside the linear regime where the source voltage is being driven outside the linear regime, and this gives rise to a contradiction because this says that Vs is less than VB, this is less than 0. But V plus minus V minus has to be larger than 0. You started out assuming V plus minus V minus being larger than 0, and assume that you operate in this regime, then you get a contradiction. So you got the contradiction that you cannot operate with this kind of mode outside the linear regime. Okay, so that is what the negative feedback system works for you. You have to work in only the linear regime. Okay, and by the same token, you can show that you can be outside the linear regime, and there's no contradiction in this picture over here. So this cannot work as a voltage follower because delta can be any number. Delta can be any number along this axis, and that picture still holds true. Okay? So some detailed argument is given in the text.